So, to summarize, a Brown clustering model consists of the following. We have some vocabulary V, which would typically be the set of all words seen in our training corpus. Again, that training corpus might consist of a few million or a few tens of millions or even a few hundreds of millions of sentences or words. We have a function C that defines a partition of the vocabulary into the k different clusters. Typically k might be around 1,000, for example. We have a parameter E of V given C for every V paired with every C. And then we have a parameter Q of C prime given C for every pair of clusters C primed and C. This intuitively is the probability of the next cluster being C primed, given that the previous cluster is C. And this is a parameter saying what's the probability of omitting the word V, given that I have a cluster C as the current cluster. So the critical question is going to be, how do we take a training corpus as input and as output produce these three things, the function C and these parameters E and Q? That's what we're going to come to next. So we're now going to describe how we derive a partition C from a training corpus. Our training corpus consists of a sequence of words W1, W2, up to Wn. Just think of this as the concatenation of all the sentences in our training data. Again, this might easily be a few tens or hundreds of millions of words. And what I'm going to describe here is a measure of how well a particular partition C fits this particular training corpus. So this is a function called quality, which takes as input a training corpus and a partition C and returns a value reflecting how well that partition C fits this particular set of training examples. This is nothing more than the log likelihood of the data, as we'll see in a moment. So this function, quality, is going to drive the algorithm that actually picks a partition C. We'll see soon how we can attempt to maximize this quality, but for now I want to describe the actual definition of this term. So what I have here is a sum from I equals 1 to n of the log probability of the ith word in the corpus, whereas before this log probability consists of two terms, the product of two terms. Firstly, the probability of omitting Wi from cluster Wi, and secondly, the probability, given that the previous word was in cluster Wi minus 1, that the next word is in cluster Wi. So we're actually going to see in a second how we can simplify this considerably. There's a number of steps here which I'm not going to go through in detail. I'll post a note describing this. So I'm just going to give a sketch on the slide of what we end up with here, but we end up with a really rather beautiful expression here, which was derived in the Brown et al. Paper. Let's just talk a little bit more about this criterion, though. So this is actually a function of three things. It's a function of the partition C, it's a function of the Q parameters, and it's a function of the E parameters. So in fact, we're going to try to maximize this function with respect to these three things. And this function can be thought of as a measure of how well these three things fit the training data. So there's a bit of a cheat here in that this quality function depends just on C, but actually E and Q have to be modified too. A critical observation is that once I have a function C, the values for the E and Q parameters can be derived in the usual maximum likelihood way. So for example, E of V given 1 is going to be count of the state 1 emitting there divided by the number of times we've seen the state 1. Or Q of 2 given 1, say, is just going to be the count of our 1 being followed by 2 divided by the count of 1. So if I fix the value for C, this partition, I can read off counts like this. I can read off the number of times I see the cluster 1, the number of times I see the word there in that cluster. Or I can count off the number of times I see cluster 1 followed by cluster 2. And these relationships hold because if I fix C, I still want to maximize this function with respect to E and Q, and this will be the values for E and Q that maximize this function. This insight is critical, and it leads through a few lines of algebra to the following form down here. So I have two terms here. G is a constant, so we can ignore this because we're going to be maximizing this function, and this constant is insensitive to the partition C. But what we end up with here is a term where we sum over all pairs of clusters, C and C primed. I look at the probability of seeing C followed by C primed in the corpus, and then I look at the log of P of C followed by C primed divided by P of C and P of C primed. How are these P's actually derived? Well, I can read off these counts from the corpus. So if I see, for example, the dog saw the cat, let's say I have some function capital C which I'm trying to evaluate, and say that maps the word the to 1, dog to 2, saw to 3, the to 1, cat to 2. Having performed this mapping, I can calculate the number of times I see C followed by C primed. So for example, n1, 2 is equal to 2 in this case. Or I can compute the number of times I've seen a particular class. For example, n2 is equal to 2, and so on. So I can read off these counts directly from my corpus once I have that function capital C, and so I can estimate these probabilities. So what I'm describing here is a mechanical way to go from a partition C to some value, which is actually equal to this likelihood. And it involves just computing these probabilities, the joint probability of seeing C followed by C primed and the marginal probability of seeing a cluster C, and then computing this expression. This identity just follows through a few lines of algebra. So that's the most important point, really, that we have a simple way of evaluating a clustering, and it has this relatively simple form. And actually, just very briefly, for those of you who might have seen some information theory, this is actually the mutual information. But again, I should stress the main result in this slide is that we now have a way of taking a partition C, so some assignment of words to clusters, and evaluating the quality of that clustering. So this is a function that will take a clustering and measure how well it fits our training corpus, and it's derived through likelihood. It's basically going to be a measure of the likelihood of the corpus under this particular clustering. And again, the derivation from this line to this takes a few times of algebra. I'm not going to go into the details of that. We'll post the original paper or a note explaining that in more detail.